Today, we have quite a bit to unpack in the spirit that I find tedious to watch when other people do it in front of me, which is it's just lots of algebra. I hope I give you the ideas. The methods are deep and they're used every place in theoretical physics, chemistry, mechanics, biophysics, robotics, whatever. The fact of life is that, very crudely speaking, there is only one problem we know how to solve. It has that various names. So we either call it harmonic oscillator, or we call it a Gaussian, or we call it something else, but basically, or we call it Keplerian ellipse, which is a rewriting of harmonic oscillator. This problem we have since the very beginning of science, which I think is probably Babylonians in a sense that we do it. What the Greeks got out of Babylonian kind of physics was they realized to describe the motions of planets, they were actually not moving on perfect spheres around stationary flat Earth. They seemed to do something a little bit more complicated. And they invented a method, numerical method, which is called method of epicycles. And when I was in high school, epicycles were ridiculed. Old-fashioned thing as opposed to the deep insights of modernity. But I'll teach you epicycles today. So it's really not very fair. So what epicycles are in a modern parlance, they're called perturbation theory. And by perturbation theory, what we always mean is that we have some problem and in some coarse way, we can make it into a circle. Or to say it a little more fancily, we are able to analytically solve some approximate version of the problem. And we have very good intuition about that. And, our intuition is that this thing is really like harmonic oscillator, but it's moving in the air, so there's some friction, or we are, applying some electric magnetic fields to impart some energy to it. And those are finer effects than the very coarse effect. So the strategy of what's called perturbation theory is to always find a good backbone for what you're looking at. If you are doing something according to this approximate rule, you're doing okay, but you're not doing very well because the true trajectory approaches you and goes away from you, etc. So you have to describe that. Now, whenever you have periodic motion, time periodic motions, then you immediately realize that you're supposed to describe everything in terms of Fourier modes. Now, you all have seen Fourier modes, you have used them, and we will go back to them in more depth also in this book. So Fourier mode says that, if I look at my motion, it looks like I'm going around with a period t, but actually there is some breathing of the true trajectory compared to my trajectory, which is periodic. And that I can mock up by adding another epicycle, another circle. It's called Fourier component, which says that this periodicity, with double frequencies of half a period, I can account for that deformation. So what I really move on is not a circle, but something that looks like a seam of a baseball or tennis ball, where you have something that's, that's an extreme example, but the second component is very big in that case. And then if that doesn't work, I have to add another periodic function of period 3, 4, 6, and I have to compute coefficients. And if my motion is smooth, you can prove that the series is very nicely convergent. It's exponentially convergent in terms of coefficients. So that's what people did in 18th and 19th century when celestial mechanics using Newton's laws were all the rage. They started adding extra Fourier modes and getting more and more accurate descriptions of motions of bodies in gravity beyond the 0th one, which is called Keplerian ellipse. So that's the first idea that comes from 19th century. The second idea is so-called secular expansion. And I actually don't know what secular means. But the meaning is following. When you have a system that you're forcing outside with some frequency, then if that frequency has nothing to do with natural frequency of the system, so you'll do the swing as an example, swing in a playground. If the child is trying to move by the natural frequency of the pendulum that she sits on, and you are an absent-minded, let's say, father, and you just push the swing whenever you happen to push it without any relation what's happening, then that will average itself to 0. The swing will stop because you'll be just kicking it all random directions and the child will not get any swing into the motion. So to be able to excite a swing or to be able to remove a comet from the asteroid belt between Jupiter and Saturn, you have to kick that thing at the right times. And so it means you wait until it comes back, after its intrinsic period 1, that's most efficient, but maybe 2, 3, 4, and then you hit it. And if you do this in harmony with the natural frequencies of the problem, you will actually be exciting the system. The swings will get longer and longer. And the asteroid will be kicked, you'll be kicked out of the rings of Saturn if you sit on rational frequencies. And when you have billions of years, to do this, it built up. And that's why we have these beautiful rings that you see in celestial bodies. And that's why there are also kind of empty areas in between planets in this asteroid belt. And that's also how you take some chemical and you disassociate it with some collection of molecules that's sitting stable. If you hit it with just the right kind of light, with right frequency or microwaves or whatever, you might excite it so much that eventually a thing will fall apart because the oscillations will be too brutal to maintain it. So the idea of secular expansion is that when you do your perturbation calculations, you must make sure that things don't explode if you know that your system is not exploding. And right now we are looking at systems which have dissipation terms in them. So they're designed, and chemical, biological systems are designed to be this way. You cannot excite them arbitrarily. So that's the second idea. So I'll try to get that through, and I'll do some algebra, but book does it in detail, and you have to do it in detail yourself. And it's tedious, and in real life, you do a few turns by hand just to get a feeling of what the problem is. And then what to do is you write the program and do it. So for example, my own PhD thesis, it took a couple of years to write this series. My perturbation series had nominally 720 terms in the expansion. Today it's down to 10,000 terms. And each term you had to compute And it was, let's say, 10-dimensional integral with lots of incredibly complicated structures. So it was enough to do PhD and even enter a textbook. So that's how it works in real life. And almost all, at least theoretical physicists, have to do first or second order perturbation theory. And some of them do high orders, even arbitrarily high orders. Today we'll stay at first and second order, just to get you feeling for the method. Once you understand it, you can apply it to your problem. So we are looking at nonlinear oscillators, and there are examples, the kind of paradigms. So one example is van der Poel, which we did before. So what it has friction, but then it has a nonlinear factor in front of friction, which varies the sign. So what that says is that if x is too small, then your friction is anti-friction. You're actually pumping energy in the system. Something very special happens when the factor is 0. You're in a borderline between pumping and not pumping. And if x has gotten so big that this factor is significantly positive, you'll dissipate energy and you'll start getting pulled back in your system. And this clever system has a parameter. In the last lecture, we made this parameter very large as an example that you can have a periodic block behavior, you can have a biological or electronic clock, which has sharp periods. But if you look at the hand of the clock, it moves slowly, it bursts, it jumps very quickly, it moves. So that was an example of strongly nonlinear oscillators. Now, very many problems of this engineering kind, electrical engineering, but also celestial mechanics or chemistry, have this structure that if you don't look very closely, they're harmonic oscillators. So they have the usual harmonic oscillator term, but there is actually some effect you have to account if you're not blind. So this one cares about dissipation and velocity. Now, if you're doing quantum field theory or quantum mechanics, dissipation is a difficult concept. Quantum mechanics is designed for mechanical systems without energy loss, where you have perfect energy conservation. So there you have a nonlinear term, which is only in the strength of the field. And in quantum field theory, this is called phi-4 theory. This is the simplest scalar field theory before you learn about electrons, photons, gluons, etc. This is the simplest kind of example that there are nonlinearities. And what those physicists are used to is to say, the basic behavior is oscillatory, but there is some weak nonlinear term. For example, in quantum electrodynamics, this epsilon is 1 over 137, which is the value of fine structure constant. In engineering, applied math, there is a German professor rather than again studying tubes called Duffing. And these are examples of this kind of equations that we will concentrate on today. So van der Poel, if this was 0, then harmonic oscillator has a center. It has one equilibrium where velocity and position are 0, both things are 0. Nothing happens there. For any other value, you run on a circle. So you expect the center. Now, the moment you have a dissipation term or energy pumping term, as it so happens, you cannot stay on a circle. So what happens in these situations, if you start someplace close to the origin, and the natural unit in the scaling, is 1. When x squared equals 1, something happens. So here is 1, 2, 3, 1, 2, 3, -2, -3. And if you start someplace, this is designed in such a way that the energy is being added to the system until you cross the critical threshold. So you spiral, and it turns out you do this very slowly. So if you put it on computer, you'll be spiraling quite slowly, but there is no center. It's the flow in which you have, nonlinear repelling center, so it's very slow expansion. And you keep doing it, and it turns out, which is, problem sets and calculation, the balance between dissipation and pumping energy in is actually at radius 2. So there is a limit cycle, radius 2, that you also slowly approach. And that's what happens if you start from inside. Now, if you start from outside, then, this has positive sign, or if I put it on the other side, it's negative sign, so it pulls me down. And I spiral in also quite slowly for small epsilon. And for epsilon equals 0, I don't spiral, I just have centers. So that's an example of weakly nonlinear oscillator. If you don't look carefully, it's oscillating, but then if you start looking at the amplitude oscillation, it's doing something. And that's what we would like to understand how to do. Now, the basic idea of perturbation theory is simpler than this application. It has infinitely many applications, but it's certainly simpler than what we are looking at right now. I will switch to an extremely good book, which is much higher level than what we are doing in this course, book of mathematical methods by two extremely good mathematical physicists, Bender and Orthrug, and take an example from them. And it's a very simple example that you can solve in many ways, but it illustrates the basic things. So look at the cubic polynomial. So you have cubic term, no quadratic in this example, just linear. And when you look at coefficients, they're suggestive. There is a large integer part and a small decimal part. And all you want to do is you want to find the roots of this polynomial. So now you do something that seems like complicating life. You say, I'll solve a more general problem. Now, you could say, what do I care about roots of cubic polynomial? That's for some childish math course. But it turns out that actually almost everything we do when we solve physical problems like eigenvalues of hydrogen or helium, or we are studying lunar motions, etc. Eventually, we reduce them to solving for the roots of polynomials. So this is not so challenging as it seems, but the example is very simple. So let's generalize this problem and say, what happens if I add a small term, epsilon, to something that is easy to solve? So the idea is you have a small parameter, but it's a good way to start many of these theoretical problems where you don't know how to find the solutions. But this epsilon in this particular example is 0.1. And now we try to solve this in terms of a perturbation series. This happens very, very often. I write X, and I'll drop this but it's a function of the parameter. And I just say, well, it's a small parameter, so why don't I write it as a series of coefficients times parameter. So if there was an n factorial, 1 over n factorial, and they'll be called Taylor series, but just a series. Here it's more convenient to do it this way. And then I can see, do I know how to solve for n equals 0 term? That's the basic term. So for n equals 0, I have coefficients in the series. Well, I'll call them xn, I suppose, in this case, but I have that x cubed minus 4x, So this is the 0th term in here. So that means I just set equal to 0. Right-hand side 0, well, it's linear in x. And obviously it's x minus x squared, x plus 2. So this thing has 3 roots. This cubic polynomial I know how to solve without any numerical pain. And they are these coefficients here, minus 2, 0, 2. So the moment I try to solve my problem by an approximation, it turns out, because there'll be 3 very distinct solutions, very far apart from each, I immediately find that I have to solve some number of problems. And each one of them will depend on, in this case, which route or which solution I'm taking. So that's very important. It's kind of the basic thing you do when you develop chaotic theory of chaos. You discover there are distinct solutions of your problem. I'll teach that in an adult level course. And then for each one of them, you'll have perturbation theory. In quantum mechanics, this means that I'm looking at some energy eigenvalue. Without external electric or magnetic field, I'll have some easy to compute spectrum. Where I add this external perturbation, each one of them will split, and they'll split differently. So I'll have to solve problems separately for every solution of the bare bone problem. Let's just run this up to the second order. It's easy enough that I can do it. And I have to do it for one case. So let me do it for the eigenvalue minus 2, root minus 2. There are 3 of them. So I say, A0 is minus 2. That's one of the 3 cases. I will now look at solutions around there. And what I'll do is, this is the first case, so x1. Its expansion, I know the 0th term, it's minus 2, I just computed it. But now I have to compute coefficient of the linear term and quadratic term. And you can do this to any order you wish, and people do it to 10, 100,000 order. In the simple cases, it's easy to go very hard if there's some reason. Now, why would you do it for high order? Sometimes you can measure it, and sometimes you need to know whether this method is internally consistent. In other words, is this a convergent series that you're computing? So you know how big are the errors of your computation. Then I have to compute x3 but now in a neighborhood. So it's a small perturbation from -2. So the cube of this guy is this term cube. And then the archenemy of Herlock-Sholmes, Dr. Moriarty, is doctor because he has written the ultimate, and this is true according to the book, the ultimate treatise on binomial theorem. So we use Dr. Moriarty's binomial theorem, as we are taking it. So I get 3 times -2 square, the first guy 2 times. And now here, I'll keep these terms, right? Or I get 3 times the A0 only once, and everybody else is proportional to epsilon, but now it gets to be squared. So I can stop my expansion here. And I can forget all the hard terms because they're higher than epsilon square. So this, now I collect terms, this is 8. Then linear term, there is this linear term. So that's 12 times A1 epsilon. Then up there's also quadratic terms. So it's 12 times 3 times 4. A2 epsilon square, dot, dot, dot. Then here I start with 12 times epsilon squared times this guy squared. So A1 square E epsilon square plus dot, dot, dot. And to get my equation, I have to subtract this. So I write down -4 plus epsilon. The linear term, that's now easy. -4, the first term is -2, -4, A1 epsilon, and then -4, A2 epsilon, just writing this out, multiplied by -4. Then I have terms of order epsilon, so I get -2 times epsilon, and then I have to keep only one term there. A1 epsilon square. I add it up, I add x cubed plus linear term, and then I also have to add, this term here. And the sum of that should be 0. And now if I've done it right, I get 0 on the left-hand side because that was the equation. Then these guys cancel, that's good news. We have taken care of A0 already, so that's the only picking up corrections. And, up to you to check me, or Bender and Orsa. Why did we complicate our problem? We had just numbers, and we made this into a continuous function of a small parameter. Well, any value of this parameter is okay, which means that the factor in the series of any power epsilon has to be separately 0. So that was the whole idea. Epsilon is arbitrary. Things have to add up to 0. So we look at first at terms down here. these guys and those guys separately. So I get 8a1 plus 4 equals 0. So that says that a1 is -1/2. Then I look at the next term, epsilon square. So that worked out right or wrong. It's up for you to catch if I'm wrong, but not right in this lecture, I don't think. Well, if you're so fast, all power to it. But you know, this depends on A2, but we have already computed A1, and that's the whole idea of perturbation theory. To compute the next term, you use all the terms that you already have computed. So it telescopes itself up. So that's same as 8a2 plus 1/2 from here. Minus, square this, 6/4 equals 0. And that's solved by a2 equals 1/8. So that means for root -2, I have my perturbation expansion, which says that x1, the first solution out of 3 distinct solutions, is the bare bone solution -2, linear correction, quadratic correction, and as many of these guys as you want. You can do it. x2, you know, that's the other root. So you have root 0. There are 3 roots. So root 0 and root +2. So now that's same calculation just around the other root, and it turns out to give you +1/2 epsilon minus 1/8 epsilon square plus whatever. And the last root was 2. And now something happens which is a real life story. This is, you know, the reason why I chose to take this particular example. You compute a correction, it turns out to be 0 times epsilon. Here, for some reason, this guy was 0 and only had linear correction, but now this is 0. And now you get anxious. The next correction is 0. Plus, turns out the next correction is 0, and you say, uh-oh, you know, what is the likelihood of world parameterized by epsilon real number that you had something that doesn't depend on epsilon, at least to, you know, first 3 orders? You know, how likely this is to happen? Very unlikely. It says you have not been thinking. And the reason why I love it is because the project on, you know, Euclidean field theory I'm doing together with my graduate student, Han Liang, this happened to us. Exactly. Not only did it happen to us, it just happened for the root which equals 2. So it turns out the theory that we study, which is like 5-4 theory, scalar field theory, every calculation has a factor of our parameter, which is, you know, instability. We are looking at chaotic field theory. At 2, everything is actually 0. So we did something stupid. So now what you do, this is now a real life situation. You go back to your case and say, well, obviously I was being a fool, because when I look at it, I have an exact solution. I don't need perturbation theory. And this happens all the time whenever you have a symmetry in a problem, because symmetries have this way to enforce something to all orders of corrections. Symmetries, when they're exact, like rotation, translation symmetries, they're very, very powerful. So it means we have missed something very fundamental about our problem, which is a symmetry. Now, when you are taught things in physics, somebody has done all the pre-digesting of the problem for you, so they obviously have a symmetry. So when somebody tells you about hydrogen being like, a moon around the Earth, or Earth around the sun, there's obviously rotational symmetry hidden in the problem, even though your solution is ellipse and it's not symmetric. So you go back and you look at this and you say, well, okay, so I was looking at this thing and 2 is exact. So what happens if I put this solution into my equation? Right, so I'm looking for the roots of this polynomial. So just put 2 in here. As every high schooler can see, this indeed adds up to 0. So that root is exact. So what are you supposed to do? And, as a physicist, you will say, there is a symmetry which I didn't see. And this is what happens in both classical mechanics and quantum mechanics. You first learn that Kepler used Tycho Brahe's data to show that motions of planets are on ellipses. But it took 2 centuries until Runge, a German physicist, mathematician, discovered that not only do Keplerian ellipses go around the moon, but there is an extra symmetry, rotational symmetry, saying that there's an extra vector called Runge vector that for Newton's potential, 1 over R potential, and only for that potential, so it's called dynamical symmetry, has preserved orientation. And the consequence of this is that ellipse is a solution, but it doesn't precess. It, just stay where it is. So it's a hidden symmetry. So, that's a discovery. And for example, we discovered that in our field theory, there's a symmetry which basically says that there's a parameter like this epsilon, but when it's larger than some critical value, everybody is unstable. When it's smaller than critical value, it's stable. And when it's exactly critical value, things vanish. And we discovered, computing lots of perturbative corrections, which in this case I call periodic solutions or periodic orbits. So that means that there is a solution. So that means that I know one of the roots, so I can write it out explicitly. And the remainder is a quadratic solution. I multiply it out, I get x3, I get a linear term, ax squared plus bx minus 2x squared plus 2ax minus 2b. This is 0. So that means, that what I call b is actually minus epsilon, comparing it with the equation. The linear term tells me that a has to equal to 2. I put it in here to get that. And that this actually is a quadratic polynomial times a known root Now, quadratic polynomials, you know how to solve. So I won't do it for you, but you can do it just for fun. When you find a root, there'll be some kind of square root. And let's say there'll be some number, but we can divide everything out. So it's plus, and there's some constant and some epsilon here. And, you know, some other term here. But the main thing is that when I solve this equation, I have a square root here. And whenever it's again, Dr. Moriarty binomial polynomial, whenever I have something that's a plus b to any power, which could be either integer or rational, in this case, power 1/2, I can do a Taylor expansion of it. And, you know, that's why I'm getting all these powers of 1/2, 1/8 in here, because, you know, I can solve it analytically. I don't need perturbation theory to do it. So I did this in, you know, maybe too much detail, just because I personally am impressed that I missed the symmetry of in my quantum field theory. And this was exactly how we found it, by looking at perturbation theory. And now I will redo it the way it's done in Strogat's book, because there it's done in the context of time-dependent trajectories, because we have a dynamical system. So we have state of the system, which is in this case, you know, one-dimensional, but it could be many-dimensional at time t. And we say, well, in my particular example, I'm looking at weakly nonlinear oscillators. So oscillator itself is a good approximation to start with. And then I do perturbation theory, but now, you know, I'm describing something. By perturbation theory, it means I just add sum of all these terms, you know, perturbation series. But now every coefficient depends on time. You know, I have to find a good small parameter, which you usually can easily figure out. So there is correction, which is linear in X. So you have to have bare bones, which everybody can get, but you're more sophisticated and you can get more and more accurate answers by computing extra terms. And now the new twist, they're all time dependent, so they'll have to satisfy. And our application will be to look at weakly linearly. First, we'll do a linear problem, because in chapter 5, we'll learn how to solve all linear problems. But then we can do it for nonlinear problems. We take harmonic oscillator. And the simplest way to screw it up is to make a damped harmonic oscillator with damping parameter epsilon, which is now assumed to be small. Now you go back to chapter 5. And you find, you know, this problem can be solved, and here is the solution. So it has exponential, and that's what you expect from damped oscillators. You know, linear problems only have exponentials of sines and cosines as solutions. And if you're damping all the time in the same way, your state should go towards 0. So it should be minus epsilon t. And this 2 is chosen, so you don't have funny factors here. But it's mostly oscillating. That's the main thing. So damped, not over damped, but kind of under damped oscillator. So that part will have a solved. But because, effect of this term is changing all the time, so there'll be sine t, but then it actually cares about this damping term. So that's exact solution. I put it here because we want to compare. Whenever you're doing perturbative problems, you first test them against something that you actually know exactly. So this is a typical situation, especially if you're writing code. Please make sure that exact problems are solved. Let's do the perturbative solution. So perturbative solution says, I write X as a series, easy part harmonic plus few, and we'll only do the linear term right now. And now what I do is I stick this into the equation. So I look at the acceleration x0 plus epsilon x1, and we'll drop higher terms, plus, this is the field twice differentiated and field written again. And then I have 2 epsilon, so let me emphasize epsilons. 2 epsilon times the first derivative, x0. Now, if I add next term, that's already overall epsilon squared, so I can drop it. So now, I first take the epsilon equals 0. So I remove everybody. Only thing that survives is harmonic oscillator. So I know how to solve that. So I have x equals 0 is x dot plus x. And this is the 0th order solution. Then I take epsilon to the first power. So I collect these 3 terms. And what I find, and this is the general structure of this problem, I find a part that looks like harmonic oscillator. So, from here and here, I always have this thing. But then there is an extra term showing up, which is minus 2x0. And this is, again, what you already saw about perturbation theory. The successive terms are written in terms of stuff you already know, plus corrections. So I already know x0. So what this is a harmonic oscillator, which I'm forcing externally by already known solution x0. So this is oscillatory solution. So this is going to be an external oscillatory crank that's affecting my x1 So, X1 would like to have its own periodic solution, but it's being forced by periodic solution that I already know.
Excuse me.
Yeah.
Why is the x0 not x0 dot? Like, it's in the derivative.
Thank you, of course,
Oh, okay.
This dt x0, I made an error as I always do. Thank you so much.
No problem.
So now, a few little details, but basically what now happens is that I know how to solve harmonic oscillator. So the solution is sines and cosines. I'll take a particular solution so that, initial conditions so that x0 of t equals sine t. Now, parenthetic remark, all these problems are solved much better in the complex plane in terms of exponentials of e to the it rather than sines and cosines, but because this is a baby course, we don't do that. But really the important thing is there is some very simple structure if you express everything in terms of the natural solutions of this problem, which are complex exponentials. But if you add them, subtract them, you get sines and cosines, that's fine. So if I take this, means I've chosen initial condition. It says x0 equals 0, 1, right? Because derivative of sine is cosine. So that's initial condition, x0 at time 0, sorry. So that I put in here, and that can be solved. And you find that x1 of t is minus t sine t. And now, we plot our solution. So our solution to the first order in perturbation expansion is the boring ordinary behavior plus first perturbative corrections. And if I plot it, so let me draw a little box. This is oscillatory, so I want to put x-axis in a half of my plot because I'll get as much stuff above as below. So this is my time. And this is the amplitude x. So x as a function of t. And now what you'll find out is that it'll start out, this will be small corrections, so it'll be dominated by this. And then it'll be okay until I get to this being of order 1, then the perturbation starts really interfering. So, okay for ET for short times, epsilon is small, but t can be arbitrarily large. So the moment that t overwhelms epsilon, so it's of order 1, what happens is that this term starts oscillating between linear envelope t diagonal and minus t diagonal, because now amplitude is going bananas. And I find out that this solution oscillates and it oscillates, wildly, because it can go all the way up to E times t, and that can be arbitrarily large. So there is some kind of envelope here. So that's a perturbative solution, but I happen to have exact solutions. So what does the exact solution say? Here is the exact solution. So it said, yeah, you should be oscillating with this period. And it's roughly, period is roughly 2 pi, because this is a small correction, this minus epsilon square. So that seems okay. But it's a dissipative system. So you have to die. You're not adding energy to it. This is a damped oscillator. So there's an exponential. And my solution is totally wrong, because in the beginning, if I plot it, on a piece of paper, they'll look pretty good. But then, when I get to this order 1 effect, then my solution just keeps being damped. It has a well-defined period oscillation, but its amplitude is going down. So it couldn't be more wrong. And that's the big problem with perturbation theory. The big problem with perturbation theory is that it's kind of designed, and you can prove its convergence sometimes, not always, for small epsilons. But you care about its convergence for large epsilons. So this is not so good. So what to do? There is a bag of tricks. Everybody encounters this problem. And what is the problem? The problem is that when I look at my function t, it has an exponential time scale. So it says that when t is larger than 1 over epsilon, and then I will be overwhelmed by dissipation, and it has an oscillatory time scale. Now, these oscillations are fast. These guys, I have to wait a long time because epsilon is a very small number. So if epsilon is 1 in 1,000, I have to go through 1,000 oscillations where this gets to be a noticeable effect. So there is a slow scale and fast scale, time scale. So this fast scale, the way it's done, period is 2 pi. So for our rough purposes, this is of order 1. But the long scale is, I have to get to the time which, when epsilon is small, is very long time before I start seeing this thing. So now the book explains, there's lots to unpack in this chapter. There are 2 scales. And in 2 timing, you say, look, this thing is moving very fast compared to a long time scale. So there is no relationship between them as far as I can tell. So let's assume they're independent. So what you do is you write your equation as though there are two independent times, even though there's only one in a differential equation. The differential is respect to two, and it's perfectly good. But I don't have the time to cover it, so read about it. It's fine. And I'll go to intuition that's very important in quantum mechanics and theoretical physics. So this intuition is, the ideas are probably already understood by Laplace much earlier, century ago, but in the 1920s, quantum mechanics was a working thing. There are lots of graduate students getting their PhDs. Each one of them opened a new field of physics, and some of them got Nobel Prizes. And three people in 1920s called Wenzel, Kramer. So Kramer was Swedish. Bourguignon, Wenzel German. An excellent French physicist, WKB, made an approximation which enabled him to make sense of quantum mechanics of Schrödinger. It's already in Schrödinger's paper in some sense, and Heisenberg. And they said, but hidden behind quantum mechanics is classical physics. And the way this works in quantum mechanics is that quantum mechanics on large energies and scales has lots of little oscillations that if you cannot measure femtoseconds, you cannot see, but you can see the average motion, meaning the amplitude of the cloud. And they said, well, when I look at my solutions, they look like just ordinary oscillations, saying, forget science for a moment, saying, I have an oscillation because Schrödinger equation looks like that. It gives me oscillations. There's an amplitude called little r here. So this is real number between 0 and whatever. And oscillation cosine. And now this time is measured in a very small units called Planck length or Planck constant, or Planck time scale. I don't want to go into details. So there's very fast oscillation. And then there is a slow drift of the phase and slow change in the thing. And let's assume that. So these guys, as far as fast motions are constant, but if I wait long enough, like 10 to the 12 quantum mechanical oscillations, electron going around the hadron something, I will notice that there is a slow behavior on this thing. So that's idea number one. The idea number two was that if you write this, in terms of, I'll write again, in terms of cosines and sines, each one has some coefficients. And assumption is that these guys are slow compared to this frequency, which is fast. So when I take a derivative of my observable then I can change the variables in the slow and fast tau and big tau. So I can write it as derivative between respect of two things. Now, if you're getting headache looking at that, you're absolutely right. Lots of thinking has to go in showing when this is good and when this is crazy. But empirically for our problems, it works quite well. So that means now when I write my differential equation, which is harmonic oscillator plus nonlinear terms, I'll have to take derivatives, this derivative square with factor epsilon. There'll be mixed term. And then two fast derivatives. Now I'm writing perturbation theory coefficients already, like we have done before. And when you do this, you'd see what we have already seen is that there is an equation that pretends nothing is changing. It's always the same. That's my little short time myopic calculation. I'm harmonic oscillator first step. But then when you go to the next order, you get this harmonic oscillator like we did before on the left-hand side, but on the right-hand side, you get driven by stuff because that is mixed derivatives of x0. So that has same structures as we had before for the damped oscillator. And now this one I know how to solve. I know the solution is a sine. These are the mixed derivative and the first derivative.
Yeah, you mean d capital T and tau? D.
Yeah, one is t and one is tau.
Thank you, Professor. And then what's written after that?
And it's in Strogat's book. And then I pick up the linear term from here, I think, from here.
Oh, yeah. Okay.
So you got mixed terms. But the main thing is that now we know x0, so you can stick it in here. And now what will happen is when I substitute these things, I will get, cosine term, sine term. For some reason, I interchanged them in my notes, and then when I'm taking derivative, the first derivative with respect here, I pick up either derivative from this term with respect to long time. The short terms don't have anything, so I pick up this kind of mixed thing for the coefficients, where this derivative is respect to the long time, and all of the short time behavior is here. So the thing is driven just like we did before, and there is a minus sign because one derivative gives a minus sign. And now comes the secular thing. These coefficients must vanish. That's a secular method of secular expansion. Otherwise, this will explode, and we don't want that. So that means that, that means that both A as a function of long time is an exponential in the long time. B as a vector of long time equals B0 minus 2. So that's the essence of all these calculations. No secular terms. And that culminates in a very general method, which is what we actually use in practice. The very general statement of all these problems is that how you do them is you do them by Fourier analysis, in other words, expansion in epicycles. So a very general statement is that if you have something that's harmonic oscillator, plus some function, and there is a small parameter in problem. So in examples we looked so far, small parameters was the ratio of the fast and slow scale. In physics, this slow parameter tends to be Planck constant, h bar, in quantum physics. And then there is some nonlinear function of x dot. That's how we started today. We had several examples, van der Poel, we have Duffing, and the simplest was the linear damped oscillator. the basic idea is that when you write these equations in two time scales, you will end up looking at stuff that has these driving terms on the left-hand side. You know, Fourier terms, which go very fast, multiplied by the factors which only depend on the short time scale. So the general stuff in the expansion will get, on the left-hand side, everything will look harmonic oscillator, but the driving terms will have the structure of derivatives, you know, if your solution is Brillouin solution. The magnitude changes with time and the phase drifts with time slowly. Then you will have to take derivatives with respect to long time of these two coefficients. And that will give you typically something that has derivative of 1 sine, and then plus the long scale plus, and then you have to take derivative of this term, which will give you derivative of phase, and then cosine of tau plus theta. You will get driving terms systematically, you know, like we did before, which are oscillatory, and they'll be multiplied by the functions of the slow variables. And then you have to, so that comes from this side, and that has to be balanced against epsilon. You know, when I look at some correction here, and they'll be balanced against expansion of this guy. So now what you have to do is you have to expand this as a Fourier series, expand, you know, sine k theta, cosine k theta. That's what Fourier series will give you. And then you'll have to make sure that secular terms don't work. So you'll compute these terms. The method of averaging will enable you. So averaging, whenever you have solution, average it over 0 to 2 pi in the fast variable times some trigonometric function that comes, you know, this one comes from expansion. And there'll be another one that comes from these H bars of various kinds. So, you know, kth Fourier coefficient, let's say cosine k theta sine theta t cosine theta t. And you have a bunch of these integrals to compute, which are compactly written as, you know, sine to some power, cosine to some power. And they're all computable. They're simple trigonometric functions. The idea of these computations is that your elementary trigonometry, this is very fast, very sketchy, but it's described well in the book. You know, if you have an odd function like sine theta, what does that mean? That means that you're looking from 0 to 2 pi, a function that goes up and down. So the odd functions will be 0. If you put k here, k odd, you have exactly as much above and below the line to get zeros. So lots of average terms get just destroyed by symmetry. If you're looking at even functions, that doesn't work because sine square is a positive function. So, if I plot it, it starts at 0. It's 0 here, it's 0 here, but then it looks like that if you compute it. And, trigonometry tells you that this is actually cosine of twice the period. But that means that its average value will be 1/2. And all other averaging works like this. You get these coefficients, so you can do this. And in this way, you get the nice result that was missing at the very beginning. So at the beginning, we had this intuition for van der Pol that it's something that if I start close to the origin, I slowly go out and I eventually get stuck at an asymptotic value of 2. Now, if I plot that as a function of time, which is done in the book, I actually get precise description. The oscillatory function just oscillates. Tuck, 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 tuck. But its oscillations go to asymptote, which happens to be 2 in this case, but it doesn't matter. And you find out that this is described by slow dynamics there. And this period, that's your fast dynamics. Now, when you're looking at something that whizzes 10 to the 11 times in every time you blink, you don't even see it. That's what happens in quantum mechanics. And you only see these envelopes, which typically tell you what's the probability that you detect the particle, such and such particle, such and such state. So that's something one should always know because, again, depends on problems that you run. There is a method of averaging that says whenever I have very fast things going on, like neurons are bursting like crazy, they burst every, I don't know, maybe 200 milliseconds, tuk, 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 tuk. But I have to walk, and that's happening on seconds and minutes, so I have to transfer information from this bursting to my motor control. I will be looking at the averaging of the bursts and their density, and that'll be the important thing. And the equations I'll develop to describe neural networks, machine learning, whatever, will capture this philosophy of getting rid of fast dynamics by averaging, saying this is just a blur, so what is it like on average? And describing the drift of these averages. What these are these things. There's a famous video I hope you've seen called Tacoma Bridge Collapse, very famous. The example of disaster in engineering, and more recent one is the Millennium Bridge in London. Those are examples of where secular terms have not taken care of. So if the wind blows just the right way to cause a vibration which is resonant for the bridge, you lose the bridge, or your magnetic train, or magnetic levitation train, etc. So lots of people have to worry about it. Depends on what you do. It turns out I have to worry about it because I forgot a factor of overall √2 in quantum field theory. Everything I told you today is extremely dangerous because there is a thing that we teach in mathematical method courses and sometimes in quantum mechanics. It's called asymptotic expansions. So, I just look at first and second term, but I didn't tell you that if you compute 1,000 terms, your answer will get better. Now, what happens in asymptotic series, and they're very, very common, I can't tell you. So, for example, in quantum electrodynamics, we know magnetic moment of electron to fine structure constants power 20 or something. Well, no, 10. And it's amazing. Best number measured and best number computed in physics for electron. But there's an argument that if I go to 137 terms, now you have to understand there's like 100 people have spent their lifetimes computing these 10 orders, so we will never get to 137 terms unless we do something very smart. You can argue very quickly that this actually is divergent series. It's like the one I showed you first, for a while it was working, then it just took off. But it takes off not linearly. It takes off combinatorially, which is fast and exponential. It's very hard to control, often impossible to control. So, and then, we do not know. I mean, maybe method is stupid, maybe it works. I claim that perturbation theory converges for quantum electrodynamics, but I cannot prove it, and other people claim it diverges. So there you learn that you have another scale in which perturbation theory works until it doesn't, and you can estimate that scale. So, experience with these things, these are imperfect systems. We only want to know them with precision 1% or 10 to the minus 3. If it's atomic physics, might be much more because quantum mechanics can be very precise, but usually not, right? So this is good enough for government work, but two timing is very scary because it doesn't make any sense. You have an equation where you take derivative with respect to time itself, well, it's derivative with respect to 2 times. How do I know this is right? Then you go and look at the books where they prove that it works for some range of parameters, etc. And averaging is the same thing. Intuitively it should be right, because if I just smear out over a very fast notion, I'll find how the averages changes. So intuitively it looks okay, but who knows, right? Whether this computational method converges, it could be that I start getting hard terms. So it's very dangerous if you're a mathematical physicist. It works amazingly well if you're a working person on the street. So don't worry about it. These things work amazingly well until they fail you, and then you'll think about it. When your answer explodes, you will know that you're screwed up. You will rethink it. But they're impressively good considering how non-rigorous they are.
So another question. So what would a physical intuition be for any divergence from, say, the series you've expanded? So what might be a good reason to understand those?
Well, this is the standard analysis and goes in usual steps. So, you want to know whether the series, this goes back to Cauchy, where the series is absolutely convergent, which means, can I put a bound on all terms in a series on their absolute value? Because often they alternate in signs, or they have complex phases, they're complex numbers, the series, or they're even, in many dimensions. So if you can show that their magnitude is absolutely convergent, meaning as you add more terms, the residual term, your estimate of the residue of the series remainder that you haven't taken account, if you can bind it, then you can show that that's going, faster than a power, then you're okay, until you get to the radius of convergence, where you have to think again, and then, complex analysis is very useful. So then it turns out that lots of series that you care about, you look at them, they're not absolutely convergent, but if you keep the signs, they add up. So any elementary book on analysis will give you examples where alternating series converges, but if you put signs on the terms, then that diverges like logarithm of number of terms or something. So then it turns out that 20 people spent between 100 to 1,000 man years full time, working 8 hours a week, 5 days a week to compute the strength of magnetic field of electron. And we have no way of knowing with present terms where that series is going to converge, but it's amazingly convergent for the first terms that we have computed. So that's real life situations. There are things that, we do not know whether quantum field theory makes sense, because mathematicians have not vigorously proven that our observables are convergent. But being working people, we compute, we compare, and it's amazing. So,
is there no general?
There is a whole part of math called analysis, which is one of the most tedious branches of mathematics, methinks, but one of the most important. People like topology, etc. But this is really important. It's very hard. So, fortunately, we physicists, engineers, scientists don't have to worry about that. It's not our problem. It's good enough for what we are doing.
Okay, so is there no general way to expand? So I do know that some people also use series with epsilon to the negative powers. And
sure, the Lorentz series, it becomes good mathematical physics. Or some things are convergent in positive powers. And, complex analysis is very, very helpful. We probably will do very little in this course. It's amazingly powerful, but tells you that you can define series with negative powers, and you can define lots of series in complex plane, which as real numbers would worry you a lot. So there are lots of tools which we will not discuss here, but that's why, it takes roughly 25 years of schooling before you're professional in any of these fields. When you add up all your years of schooling, and then they put you on the day shift, says Bob Dylan. But you have to learn that stuff too. Right now, we're just learning. We are correcting the errors of previous education, which is all linear. Until now, we only taught you about harmonic oscillator, 27 different guises. Now you have to learn that when things are nonlinear, we also have some tools, but it gets harder. And for problems that we have to deal, methods of Strogat's books tend to be perfectly sufficient. Biological clocks or chemical clocks or other kind of nonlinear systems that we have to understand to be able to do, basic chemistry, biology, biophysics, etc. Rocket science, whatever. This is pretty good. Now, if you ask a question, will the solar system fall apart or be with us forever? I think the question is it will fall apart, but it's highly, highly non-trivial question, and we are not, sure one way or the other. Over the last 2 centuries, our opinion on this is fluctuating from, being eternal to being unstable to being eternal, and right now it's unstable. We went through at least 2 cycles, starting with Laplace, through Poincaré, through Kolmogorov, Moser, Arnold, to what modern simulations of solar system that go, 10 billion years ahead tell us is going to happen. So you will go ahead and science will not be dead. There will be no time within your human lifespan in which you will run out of problems to think about. But, your toolbox is getting a little bit bigger by taking a course like this.
Thank you. Yeah.
If it's any consolation, I keep learning all the time myself, new methods. It's not like I've run out of methods.
Well, who knows? Maybe the whole solar system is a PhD thesis from a scientist from another universe.
Well, we're just a bag of water with some heavy atoms thrown in. So it's amazing we can do anything at all. So yes, I mean, a being with intelligence opposed to us can do God knows what. But this is not to be covered in this course.
Yeah.
Yes, I mean, over the beer, yes.